Very good morning, students. So in this video we shall solve few more problems from the probability theory from level 1, right? So here come the questions, example number 7 and example number 8. Two cards are drawn from 52 cards. What is the probability that they are kings and hearts? Guys, in the previous video I have shown you the structure of playing cards method, right? Completely how the playing cards are being bifurcated in terms of colors and in terms of symbols and in terms of numbers and face cards. So everything, one diagrammatical structure I have shown you in the previous video. Now based on that, so these two problems are from playing cards experiment itself. So let us see there. Two cards are drawn from 52 cards. So how many cards are drawn? 2. What is the probability that they are of kings, both the cards, and then hearts, both the cards? And tell me guys, out of 52, how many king cards will be there? From each set, 1, 1, 1, 1. Isn't it? So let us write that. Let K be an event of getting kings and H be an event of getting hearts. So probability of kings equals to. So what is the answer here? Kings, how many cards will be there? 4. In that how many cards are chosen? 2. So 4C2 by 52C2. Exhaustive number of cases. What is the value of 4C2? Tell me, 4C2 is 6. Divided by 52C2 is 1326. Next, probability of getting hearts. Hearts, how many are there? 13 heart symbol cards will be there. Remember guys. So in that 13, 2 were picked out of exhaustive cases. 52C2. Now final answer is 78. 13C2 is 78 divided by 1326. Clear? So here two cards are drawn. Let K be an event of getting both the kings and H be an event of getting both the hearts. So first of all, learn how many kings will be there from the total set 52. 4 kings and hearts will be 13, right? Therefore favorable cases. Out of 4 kings we need 2 kings, right? Therefore 4C2 divided by exhaustive cases. Out of 52 how many are picked? 2. So therefore 52C2. And the answer is 6 divided by 1326. Next, probability of getting heart. Heart symbols were 13. King, queen, jack, ace and 2 to 10 number having heart symbol. 13 cards will be there in that suit. Therefore, out of 13, 2 hearts we need. So 13C2 divided by 52C2. That is 78 divided by 1326. Clear? So let us have one more question. Look at there. A card is drawn from 52 cards. What is the probability that it is an ace card? As you all know that king, queen, jack, ace and 2 to 10 number, each card having 4 each, right? So heart symbol, having heart symbol, 13 cards, king, queen, jack, ace and 2 to 10 number, having diamond symbol also 13 and having club symbol also 13 and then spade symbol also 13 cards. Now ace cards how many will be there? 4. So straight away we can write it. Let A be an event of getting ace card. So probability of A equals to. So only one card is drawn. So ace cards will be 4. 4C1 by 52C1. Answer will be 4 by 52. Second question, not an ace. Not an ace means PA dash. Nothing but 1 minus P of A. 1 minus 4 by 52. Out of 52, ace cards if you remove, remaining all are non-ace cards only now. How many are there? 48 by 52. is the answer. Hope I am clear, guys. So A's cards will be 4, only one card is picked, so 4C1 by 52C1 exhaustive, and then not an A's, so P of A complement, which is not of A. So A complement is nothing but, logically if you think, out of 52 cards, A's cards were 4, remaining 48 cards were non-A's cards. So straight away we can write it. But here, according to the formula, it has to be calculated. P of A dash equals to 1 minus P of A, that is 1 minus of 4 by 52, nothing but 48 by 52. Clear, guys? So let us see few more problems now. I hope these two problems are clear. Look at the next two questions. Example number 9 and 10. Example number 9. Probability of player A winning a game is 3 by 5. So here probability of winning the match is 3 by 5. So let us consider that will be the event A, right? But the question is asked, find the probability that he does not win, nothing but A complement it is asked. Straight question, guys. Look at here. Let A be an event of winning the match. Event of winning the match. Therefore, P of A given 3 by 5, but the question is asked, does not win. So answer is 2 by 5. Very simple, guys. Let A be an event of winning the match, and that is probability of A is given already, 3 by 5, winning the match. And then it is asked that does not win. So that means P of A dash, A complement, nothing but 1 minus P of A. So 1 minus of winning, if you remove, remaining all are losing only, no? 2 by 5 chances are losing. Chances. Clear? Next. Example number 10. In a lot, 20 bulbs, 4 are defective. Out of 20, how many are defective now? 4. That means, what is the probability of getting defective bulbs? 4 by 20. 4 divided by 20 are the probability of getting defective bulbs. Now, one bulb is randomly selected at random. Find the probability that the selected one is a non-defective bulb. First of all, so let us consider here, let D be an event of getting a defective bulb. Write down. Let D be an event of getting defective bulb. Therefore, probability of D 4 divided by 20. So 4 divided by 20 means 1 by 5, nothing but 0.2. Now, probability of D dash they are asking it. Non-defective bulbs, they are asking it. Non-defective bulbs means 1 minus of defectives. If you remove 1 minus of 0.2, answer is 0.8, or 1 minus of 1 by 5. 4 by 5 is the answer. Clear, guys? So very simple question. So out of 20 bulbs, 4 are defective it seems. So that means what is the probability of getting defective bulbs? 4 by 20. Nothing but 1 by 5, 0.2 in terms of decimals. And then probability of getting non-defective bulbs, it is asked. Find the probability that the picked one is a non-defective bulb. That means from the total probability, if you remove the defective bulbs, remaining all are non-defective bulbs only, no? Right? So answer would be 4 by 5. Clear, guys? So this is the solution. Example number 9 and example number 10. Hope again these two problems are clear. So let us have few more problems. Yes, next two questions. A die is thrown once. What is the probability of getting a multiple of 4? And question number 2, non-multiple of 4. First thing is getting a multiple of 4 and non-getting multiple of 4. So let us consider two events. let A be an event of getting multiple of 4 and A dash be an event of getting non-multiple of 4. So probability of A equals to getting multiple of 4. What is the sample space? 1, 2, 3, 4, 5, 6. When a die is thrown, sample space S equals to 1, 2, 3, 4, 5, 6. Next, probability of A getting multiple of 4. How many? Multiple of 4 will be only 1 out of 6. Therefore, favorable cases, how many are there? 1 divided by 6. Next, probability of getting A dash, 1 minus of P of A. So 1 minus of 1 by 6. Non-multiplicity will be 5 outcomes, 5 by 6. Probability of A will be only 4. Multiple of 4 will be only one event, elementary event, 4. Therefore, out of 6, only 1 is there. So 1 by 6 is the probability of getting multiple of 4. And probability of non-multiple of 4 would be P of A dash complement. So 1 minus P of A, that equals to 1 minus 1 by 6, that is 5 by 6. Now, example number 12. Given P of A is 1 by 4. Straight question. P of A dash 1 minus P of A 1 minus 1 by 4, 3 by 4 is the answer. Straight question. Guys, with this, level 1 problems are over. Clear? Exactly. Examples 12 problems. Isn't it? This is all level 1 problems. Now, we are going to discuss about if two events are mutually exclusive, non-mutually exclusive. Mutually exclusive means the occurrence of one event which prevents the occurrence of any other event in a single trial. Right. So mutually exclusive means separate. There is no common, separate elements, disjoint events, we can say. Mutually exclusive. When two events are mutually exclusive and when two events are non-mutually exclusive in case of addition theorem, we are going to solve now. First and foremost, I would like to prove the addition theorem of both the cases, mutually exclusive and non-mutually exclusive. Later on, based on those problems, we shall calculate. This is level 2. Right? Addition theorem and multiplication theorem using. So level 2 addition theorem problems. Level 3 will be multiplication theorem problems. Clear guys? Using conditional probability. So let us have the addition theorem concept. Now all the basic problems are completed. Right? Exactly 12 questions. And there is one more example. Example number 13. The same kind of example 12. Similar kind of problem. There it is given P of A equals to 0.6. Find P of A dash. So 1 minus 0.6, 0.4 would be the answer. That's why I did not repeat that question. Clear? So now let us have the main major concept, addition theorem. Now the actual concept begins. Level 2. So let us have those level 2 concepts now. So look at here, addition theorem. So addition theorem, usually there are two cases. First thing is when A and B, two events, are said to be mutually exclusive, then P of A union B or P of A plus B or P of A or B, all the three are one and the same. P of A union B equals to P of A plus P of B. Remember, when two events are said to be mutually exclusive, one which prevents the other in a single trial. Case 2 would be when two events are said to be non-mutually exclusive. Non-mutually means they are not excluded. Somewhere there must be a common element. Common element means intersection should be used. P of A union B equals to P of A plus P of B minus P of A intersection B. So when mutually exclusive means intersection won't come. When non-mutually exclusive means they are somewhere not disjoint. They are somewhere joint. So joint events there. Therefore, the joint event P of A and B must be taken out. That is P of A union B equals to P of A plus P of B minus P of A intersection B. Now let us have the theorem number 1, case 1, when two events are said to be mutually exclusive. Mutually exclusive means completely the separate events. So there will be no common element, completely disjoint there. Therefore P of A union B equals to P of A plus P of B. Now let us have the proof. Let S be a sample space, set of all the possible outcomes of a random experiment, and then A and B are said to be mutually exclusive, one which prevents the other in a single trial. Then by definition, probability of A union B equals to, as you all know, that favorable by exhaustive. So exhaustive cases are N of S, and then favorable cases are N of A union B. So A union B means according to the union of an event. What is the formula? N of A plus N of B divided by N of S, because here A and B are two mutually exclusive events. Now split that one, N of A by N of S plus N of B by N of S. N of A by N of S is nothing but probability of event A, and plus N of B by N of S is probability of event B. Therefore P of A union B equals to P of A plus P of B. Even the Venn diagram also I have shown. Using this Venn diagram, there is another alternative. P of A union B equals to A plus B by N. So A by N plus B by N. That is P of A plus P of B. That's it. So very simple one. Alternative one it is. Usually the above one which I had written by black, that has to be done in the examination. If it is asked state and prove the two events are said to be mutually exclusive in addition theorem, or else state and prove the addition theorem when two events are mutually exclusive, you have to prove this one literally. Clear guys? So this is addition theorem under mutually exclusive case. Clear? P of A union B equals to P of A plus P of B. Totally disjoint. There will be no connection at all. Totally excluded both the events. Right? So one event which prevents the total events of others in a single trial of any random experiment. Clear guys? This is addition theorem case 1. Now let us see addition theorem case 1 problems. Based on case 1 addition theorem problems we shall do, and then later on non-mutually exclusive theorem also I will be proving it. Based on that we shall solve some more problems. Clear guys? So now till this addition theorem we shall solve problems on addition theorem of mutually exclusive events. Addition theorem of mutually exclusive events we are going to solve now. Just have a look. The theorem, very important concept guys, it is addition theorem. Immediately by seeing the question you have to identify whether they are whether they are mutually exclusive or non-mutually exclusive. Mutually exclusive means which condition should be applied? P of A union B equals to P of A plus P of B, just adding. When non-mutually exclusive case means you must take P of A union B equals to P of A plus P of B. Along with that, what is a common element that has to be removed? Minus P of A intersection B. Clear? So occurrence of at least one event we need here. Remember P of A union B in both the cases. Here A plus B straight away because there is no common element in mutually exclusive. But here there will be a common element. That common element should be removed and converted into A or B. At least one case, P of A union B. So that is the reason we subtracted P of A plus P of B minus P of A intersection B. Intersection, product, remember, and we can do it. At the same time it's a common element. That common element has to be found and removed from the total P of A plus P of B. Clear guys? So now with this I am going to wind up this video. So in the next video we are going to discuss about addition theorem case 1 mutually exclusive problems. Exclusively mutually exclusive problems we are going to calculate in the next video. Hope everybody is following the videos. So and then you are understanding each and every concept. We are very clear by just making out these videos. without any flaw we are making it. If you have still any further queries during offline sessions, we can have a one-to-one interaction, so we can again glance over of all these concepts in regular classes. Clear? So everybody is doing great. So stay home, stay safe, and don't waste your time, guys. Right? So prepare yourself in all the ways, either come health side as well as academical side also. Right? Hope everybody is doing great. Have a nice day. Thank you.